The little kids were making fun of my talk today. And by little kids, I mean the 6th graders. But you know, haters are gonna hate. And that means we're gonna do polynomial functions. And the haters and polynomial functions, there is no correlation, but I just wanted to try to start out this video in a little bit more interesting way. So, you guys took a look at the different properties of exponents last time, and lesson 2.2 is all about evaluating and graphing polynomial functions. But first things first, since we're talking about polynomial functions, what are they? In order for us to define polynomial functions, we have to first understand monomial functions. I don't know if you recall, but we've covered what monomial is before. But what is a monomial? Monomial is basically a function with a single term, right? And a term could be a variable like x, y, z, or a number like 3, 2, or it could be a product of numbers and variables like 3xy. So any single term function would be classified as monomial. And mono is a prefix that goes into anything that has to do with like a single, you know, like a monologue is a speech or some sort of an act delivered by a single person, right? And a dialogue is by multiple people. Another good example would be like monogamous relationship. That's when you are dating only one person. And what do we call it when you are interested in multiple people? You're dating multiple people under, under everyone's consent. We call that polyamorous relationship, right? And that poly indicates that there are multiple. So polynomial functions essentially just means it's a function with multiple monomial functions. A polynomial could be a monomial or a sum of monomials. This is what the standard form of a polynomial function looks like. It looks very complex, right? But actually, it just indicates this being leading coefficient. So n over here is the degree, meaning the highest exponent that's present in the function. This is our degree. In our polynomial function, we have our leading coefficient right there, which sits in front of the highest or the highest exponent of x, also known as degree. And we have our constant at the very end. So a lot of times when we're looking at a polynomial function, we like to arrange our terms in a descending order, meaning the highest, the degree, the term with the degree comes at the very front, and then our exponent gets smaller and smaller until we get to our constant. Okay, so now we're going to take a look at some common polynomial functions. First thing, when our degree is 0, that means we only have our constant present in our polynomial function. So when our degree is 0, then we call that constant because the only term present in the function is the constant term. And the standard form of constant term looks something like this. When our degree is 1, here, let me fold it up. When our degree is 1, we call that function linear because why? When we graph it, it looks like a straight line. And what's the standard form of a linear function? It is function of x equals a of 1, x plus a 0. This is what the standard form of the linear function looks like. When our degree is 2, we call that, we just went over this, quadratic function. Quadratic function, we should be we should be able to confidently identify a quadratic function. But the standard form of a quadratic function is a, oh my God, is the building collapsing? Oops. A2, A1, A0. The standard form of a quadratic function is as such when our degree turns into 3. So x is raised to the power of 3, then we call this, you might be able to identify this function already, but we call it a cubic function because we're cubing it, right? It's a cubic function. It's when our degree is 3. And the standard form of a cubic function, again, is fairly straightforward. It's just that our our degree is 3, right? So a good, oh no. This is the standard form of a cubic function. Next, if our degree comes up to be 4, we call that quartic function. So when our degree is 4, we call that quartic. And a quartic function, again, the standard form is fairly straightforward. It's just that our degree would be 4, and it proceeds just like what we've covered. So I want you to remember constant, linear, definitely linear and constant, quadratic for sure. And then when we cube it, cubic function, and then when our degree is 4, we call that quartic function. Direct substitution is literally what we've been doing when we're talking about substitution in general. When we go ahead, substitute the value of x with a given number and finding the output, the value of y. So that's what direct substitution is. But now we're being introduced to what we call synthetic substitution. Now, synthetic substitution is very useful when we're dealing with polynomial functions, because it may be too cumbersome for us to write down every single term. So what we do is, let's say we're looking at what kind of function is this? This is a quartic function, right? With our degree being 4, leading coefficient being 2, and our constant being 8. Okay, so if I were to use direct substitution and let's say x equals 3, what we do is we would literally replace x with 3, right? And just find the value. But using synthetic substitution, what we do is, I'm going to turn my camera around. With synthetic substitution, I go ahead first, put my x value right there, and then I go ahead, write all of my coefficients. So it starts out with 2, -5, -4. Oh, actually, we're missing x squared, right? So therefore, that would be 0, -4, and then finally, our constant, 8. So we put all of our coefficients in order, and what I do is I go ahead, bring down the very first coefficient, our leading coefficient, so 2 comes down, and then we multiply x value with 2, which is what we will be doing anyways, even if we're using direct substitution, right? We go ahead, put it right over there. So 3 times 2, 6, and then we add -5 and 6, then it comes down to be 1, and then again, I multiply 3 by 1, which would come to be 3, 0 plus 3, 3, 3 times 3, 9, negative 4 plus 9, 5, and 3 times 5, 15. 8 plus 15 would be 23. So that would be our value, our output when our input is 3. So function of 3 is 23. Ta-da! Quite simple, right? So let's go ahead and use an example from our extra practice workbook. I'm gonna use number 6, which is another quartic function. So function of x equals 7x raised to the power 4 minus 3x cubed plus x squared plus 5x minus 9. Okay, oopsie, that's Einstein. All right, so now they want us to find the value, evaluate when our x is 2. So using synthetic substitution, I'm going to put my x right there. And then I put my leading coefficient, and then all the coefficients in descending order. 4, 3, 2, 1, and then negative 9. Okay, this one comes down, so we get 7. 2 times 7, 14. We add them, then we get 11. Multiply 2 and 11, so it comes out to be 22. We add them, 23. Multiply 2 and 23, then we get 46. We add them, 51. And then 2 times 51 comes out to be 102. And negative 9 plus 102 would be negative 9 would be 93. No. Yeah, 93, right? 92, 93. So function of 2 gives us 93. There it goes. Using synthetic substitution is such a helpful tool, especially when we're evaluating polynomial functions, because it's so simple. All right. One more thing we have to talk about when we're discussing polynomial functions is end behaviors. Now, if you still have the graphs of parent functions we put together over the summer, you can refer to that graphic organizer, and you should definitely have that. But just in case, if you don't have it, here's the gist of it. So basically, what is end behavior? End behavior is literally behavior of a function's graph as x values approach positive infinity and negative infinity. So we're looking at how different x values basically affect the behavior of the function's graph. So for example, if let's say we have an odd degree, so such as linear, such as cubic function, and our leading coefficient is positive, then what happens? Usually, if that's the case, when our leading coefficient is positive, we know that our graph would go up, right? From left to right, it goes up. So which means as our x value approaches positive infinity, our function also approaches positive infinity. But on the other end, it also means as x values approaches negative infinity, our function also approaches negative infinity, right? But let's say, even if it's an odd degree function, what if our leading coefficient is negative? Then it's flipped. So instead of going up, increasing, it goes down. So as our x value approaches positive infinity, instead of going up, it actually goes, the function value goes down. And as x values approach negative infinity, this time around though, the function values actually go up. So with odd functions, their end behaviors are always opposite, right? So it's either they start at low and they go up, or they start up and then they go down. Now, it's a different case when our degree is even, so constant, or like a quadratic function, like a parabola. Remember, when our leading coefficient is positive, all the graph goes up, right? And when our leading coefficient is negative, it goes down. So same thing goes with, right now what I have is a quartic function. So when our degree is 4. So when our degree is even and our leading coefficient is positive, as x value approaches positive infinity, our function approaches also positive infinity. And as our x value approaches negative infinity, our function actually just goes up. So it approaches positive infinity. But obviously, it would be flipped when our leading coefficient is negative. So everything goes down. Let's see. So the first function that I have, this is from your workbook. First of all, we know that our leading coefficient is negative, and this is an odd function, which means our end behavior would be as x goes to positive infinity, our function of x would be the opposite, right? So it would go down. So our function of x would approach negative infinity, and as x approaches negative infinity, our function of x would approach positive infinity. Right, so now that we got that out of the way, we can go ahead, create a very simple table. So I'm gonna substitute 0, 1, 2, -1, -2. So these are my x values, and these would be my function of x. So when x is 0, obviously we would get -2. And when x is 1, we would get -3. When x is 2, we would get -10. And when x is -1, we will get +1 minus 2, -1. And when it's -2, we will get +8, 6. So these are the values that I have. Now we're going to use all of this information to graph this cubic function. So let's see. So when x is 0, y is -2. When x is 1, y is -3. And when x is 2, y is -10. So it'll be somewhere around here, I imagine. We're going way off the chart. And when x is -1, y is -1. When x is -2, y is actually +6. Right there. So our graph would look something like this. And what did we say about our end behavior before? We said as x value approaches positive infinity, our y value would approach negative infinity. And as our x values approach positive and negative infinity, our y value would approach positive infinity. So voila,